Hi, I'm Paige Roberts, and I'm going to talk to you about in-database machine learning with Jupyter. In particular, I'm first going to talk to you a little bit about what in-database machine learning actually means, and is it really possible with modern databases, analytical databases in particular, and I'm going to talk a lot about MPP databases, so distributed databases that work across multiple computers. And then I'm going to talk a little bit about why, if I can do my machine learning inside a database, why would I want to? So I guess the next question, once you've kind of got the idea of like, oh, okay, that's why I would want to do it. And then I'm going to get to the meat of the presentation, and I'm actually going to do a Jupyter notebook walkthrough with you and just kind of show you the code and the results. And the links so that you can go try it out for yourself anytime you wish, and then we'll get to some questions, hopefully, if we have some time. So first off, as you probably know, advanced analytics like predictive, prescriptive, with methods like machine learning and deep learning, they touch our lives every day. They're all over the place. Climate Corp is using the machine learning to increase farmers' crop yield, of all things. Philips is using machine learning to make sure that MRIs and CAT scanners and important medical devices like that don't break down. Uber is using it to optimize routes to get you a car in under 7 minutes. HP is using AI ops to optimize your network optimizations. So all of these companies have one thing in common. They're not just doing data science for the fun of it. They're not stuck in the experimental stage. They've managed to get their advanced analytics into production to the point where they're making a difference in their business. And they have another thing in common. They are all using a database. Now, some of them are doing the machine learning in the database, some next to it, but they are all using it, and a fair number of them are doing their machine learning inside the database. So how? That's a good question. First off, yes, it is in fact possible. So just so you don't think that I'm only talking about my own product, this is a vendor-neutral presentation. I will use Vertica as the examples because that's what I know. Nobody else's customers want to talk to me. I'm used to it. I know how it works. But Vertica is not by any means the only database out there that distributes work across multiple computers and does analytics at a deep level. In fact, there's a recent article that I've put a link to on here, and I will give you the PDF so you actually can see the whole link. It shows at least 8 other databases out there, and this is just one article. If you go looking, a lot of the MPP analytical databases nowadays have machine learning included as part of what they offer. Now, it may be an add-on. It may be an extra application even that they integrate really well with. A lot of times there's a little extra cost associated with machine learning, and that's legit. I think the one thing you have to watch out for is companies that want to charge you per algorithm or per function or things like that. It's like that kind of nickel and diming is just not cool, and you should avoid it. But otherwise, we're pretty good. The rest of this example, I'm going to talk pretty much specifically about Vertica, but again, assume that anything I say, almost, unless I say it's Vertica specific, it's out there. Any good analytical database nowadays has got the capability to train a machine learning algorithm, to do some data preparation, to predict with a machine learning algorithm. It's in there. It's not unusual. It's not special to any particular database. It is not. A lot of times I think people believe that the only way to do analytics is using some samples on a data lake with lots of exploration and some really serious struggling, and then to hand it off to a data engineer to put it into production and distribute it across large data sets and get it deployed on production systems. And that's just not the case. The nice thing about a database is it is the same in development, in production, in test. So getting it from one environment to the next is completely easy, like a line of code. It's not a month-long project to rebuild the work that you've already done. All of these algorithms are already built in to your to most analytical MPP databases, and these are just the basics, of course. The algorithm list keeps going. But everybody needs linear regression and some clustering and things like that. So the basics are in there, and there's often a whole lot more XGBoost and time series analysis like Surima and things like that. It's like those are in there. You can do that in a database. You can also train your model inside the database, save it as PMML, and go take it somewhere else. If that's what you need to do to get your job done, or if you want to, you're just dead set on training it somewhere else, that's fine. You can import that model into the database, and the database can evaluate it, save it, deploy it, put it to work predicting on production data right away without you having, again, to rebuild everything. So that's pretty powerful. If you have a TensorFlow graph that you developed, a nice deep learning model that you developed on GPU machines, which are super expensive, and you want to put it into production, and of course your production data flow isn't on that expensive GPU machine, you can save that graph and put it into a database and put it to work. So, all right, so I've hopefully convinced you that you can do it. Now, why? Well, I can, but why would I want to? Well, the other methods come with some problems. In particular, it costs extra. A lot of times there's a whole lot of different components. Right now, the data science project and application landscape is bonkers. The amount of components that you need is crazy. You need a lot of powerful compute. You need a lot of things that cost your company money. The other aspect is a lot of times, a lot of your favorite tools, the ones that you can be the most productive in, like Python and R, they're designed to work on a single machine inside the memory space of that single machine. So if I can only manage maybe a 1/4 terabyte at best on my little sandbox, then that means if I have 100 terabytes in my production database, I am going to have to do some serious downsampling. And I'm going to have to probably take multiple samples to try and get something like a representative sample, and maybe it's going to take me a while to move it around. My data types are going to be weird. I'm going to have to pull data from multiple locations. This is why this is a problem. And it makes your development slow. And it also makes your time to deployment slow, because once you've done your job, you've got it. This is the model. This is going to boost my company's revenue hugely or save us a whole bunch of money. This is a great model. How do I get it into deployment? Well, now I have to hand it off to a data engineer who then has to rebuild it in something like Spark, or some other method that can distribute it across large data sets and put it to work on your production systems. And that is a problem. That's not a great way to do things. You really want to be able to get to the point. I mean, right now, depending on who you ask, 60 to 90% of machine learning projects are failing at that point, where you've got a proof of concept, your model is happy, it's wonderful, but you can't get it into deployment. It may take 3 months, it may take 6 months, it may take a year. or more. And that is a problem. So how does a database help you? Well, one of the things that a distributed analytical database is good at, of course, is distributing. So all of the machine learning that is built into a database or designed to be compatible with an MPP database is going to be distributed. That means these are special machine learning models built for production-sized data. If I have 50 terabytes or 1,000 terabytes, or 10 petabytes of data or more, how do I train my algorithm on as much data as possible so that it is as accurate as I can possibly make it? Because taking a sample may be really good statistical, very typical of that data set, but you are almost certainly, by not using as much of the data as you possibly can, you are going to lose at least maybe a percentage point or 2 or 3 of accuracy. And in a business, that can mean millions of dollars lost to your company because you had to sample instead of being able to use the whole data set. And because everything is distributed, you can use the entire data set, and that's pretty awesome. Now, this also means that if I import a model as PMML and I put it into the database, it is now going to distribute that model and use it on the entire data set. If a lot of databases have a user-defined extension capability so that I can create my own special thing, it's like my company has to do this really cool thing and this is our secret sauce. And the reason it's better is because my algorithm is better than anybody else's. Well, if I take that secret, special, unique algorithm and I put it into the database, that means it's going to distribute it, and all of the other things that I have to do, all of the data preparation steps, the 100 different steps that I have to get that data ready for that algorithm, are also all going to be distributed and built in, and I don't have to build them from scratch. The only thing I have to build is the super secret awesome thing that is special to my company and to me. The other aspect of a database is not just designed to handle lots of data and lots of kinds of data. And this is kind of new. A lot of people think databases are limited to like a row and column, super structured. If it's not, if it can't, if it doesn't look right in an Excel spreadsheet, then your database can't handle it. And that's not accurate. Databases have changed a lot over the years. At this point, they can handle streaming data, semi-structured data like JSON and log files and sensor data. You can handle, you can query data outside of the database. You're actually, the query engine that works on the database's data also works on Parquet and Orc and JSON and all that other data that's nowadays stored pretty much in the same place. It's all usually stored in like an S3 bucket or in some form of object storage, and including the database data. So the database just queries it all. And all that analytics and machine learning and geospatial and time series analytics, it's built in. And that's great. All of that is great. But the real thing that differentiates, I think, in database machine learning from any other way of doing data science, doing the job, is that you can do a lot of things simultaneously. And a lot of people can do a lot of things simultaneously. So if I've got 30, 40 people drilling down on a nice BI dashboard, that's not going to bother my analytical database. It's used to that. It's used to 100 people or 1,000 people doing that at once. And over the years, it has developed to the point where we can now spin up compute and spin it back down as needed. That's a wonderful thing that like the cloud taught us. It's like you only need compute when you need it, and then you can make it go away. Well, that means you can spin up compute and you can dedicate it to a particular workload. So Training a machine learning algorithm is a good example. That eats up a lot of compute resources. It will eat up all the compute resources that are dedicated to that workload without bothering any of the compute resources that are dedicated to all the other workloads, to ad hoc BI queries, or to data exploration, or to ETL, constantly, pulling and streaming data and transforming it and getting it ready. All of those things can happen simultaneously, and that concurrency is massive. That is the thing that makes a database very different from a lot of other options. So, quick summary. What do you get from a database? You eliminate the overhead of having to move your data to somewhere else. You keep your data secure. Databases have been around a long time. They have mature, proven reliability and governance and data provenance, and they know, all of the things, security, all of the things that you really want in your data to make it trusted. They're in there. So that saves you a lot of grief. They can store the tables, the data, and the models together. How awesome is that? That means if you need to retrain your model and you want to get exactly the same model again, you can. If you want to go back and do some explainability, well, why did the model predict it this way? Well, here's the data it was trained on. There's a lot of powerful capabilities based on the fact that those three things are saved together. Hundreds of concurrent users, lots of different workloads going at the same time, nobody bumps into each other, highly scalable, high performance, which means you develop faster and you can do more iterations and get a sharper, faster, smarter model in the same amount of time, which is kind of awesome. Built-in machine learning functionalities and geospatial functionalities and data preparation functionalities and time series joins and analysis and things like that. This is pretty powerful in itself, just having all that stuff at your fingertips and not having to go somewhere else. Go get another component. Go, I got to have a time series database, and I got to have, a special Spark cluster, and I got to have this. It's like, no, it's all in your database. It's fine. You don't have to go somewhere else and go do something else. You don't have to maintain a bunch of systems. You don't have to integrate a bunch of systems. And here's a thing that you probably didn't know. Yes, you can do SQL. Sure. And that means all your BI tools are great. Your Grafana and your Tableau and your Power BI and all those things that use SQL to communicate with the database, they work. And they work perfectly because everything in a database can be done with SQL. And if you're comfortable with SQL, go for it. But a lot of people like to do data science in R or in Python. They like to use Jupyter notebooks and write some Python code and do some interaction. And we like that. And that makes us more productive if we're comfortable with the environment that we're working in. And of course, I don't even know if I ever mentioned that, but because a database is used to manipulating data, it's actually going to do your data preparation steps much more quickly and on more data. So what you were used to doing on, maybe this little quarter terabyte that just barely squeezes into your memory, you can now do on 30 terabytes. In the same amount of time, and that's powerful. The only time you should ever have to sample data is when you want to split it into like a training set and a test set. That's the only really good reason. So let's get to the meat of it, and let's dive in and actually look at an example. So this is an example that is available online. We're going to use a Python library called VerticaPy. And under the covers, it uses a client API called VerticaPython, which basically Uber created it, Twitter, Palantir, Etsy, Kayak, Good Data. A lot of folks have contributed to VerticaPython, and it is essentially a Python client for the Vertica database. So instead of using SQL, you can use Python. And VerticaPy lets you use your Jupyter notebook and make it really comfortable. So how does it work? Well, essentially the way it works is you import the library and you write what looks pretty much like Python code in your Jupyter notebook. The big difference is instead of creating an in-memory data frame and doing your steps on that, you are creating a virtual data frame. Now, the virtual data frame looks and works just like a data frame, like you're used to, but it never actually goes into memory on your machine. It never leaves the database. It stays in the database. So all of the work that you're doing on the data, including training your algorithms and every step up to that, and then using them to predict even, and evaluating them. And every step along the way is going to be done inside the database. Just like if I had Grafana and I had a Grafana dashboard and I needed to do a drill down. So I need to go and look at some more information and get broader information to display that in Grafana. Well, Grafana isn't going to do any work, really. It's going to generate some SQL and it's going to hand that off to the database. The database engine is highly optimized to execute SQL at the best possible way on a distributed system. Now, it's kind of like a DAG. It's like I just have told it what I want it to do, and then the engine figures out a good way to do it. And that's the database engine. All of your processing, everything you need to do is pushed onto the database. All you do is you write Python instructions in your notebook and tell it what to do. It does it, and then it shows you the results. That's it. That's how it works. So there's a lot of examples out on the web. I'm actually going to use the smart meter example, which is like bottom to second from the left there. But you can go out and you can look at any example that makes you happy. So the way this works is it's got 3 data sets. One is the reading on the meter. It's going to tell me how much data was consumed in this amount of time. And it's going to have the date timestamp to tell me how much time or when I got this reading from the meter. And then the weather. It's like, was it hot? Was it cold? What was the humidity? And then I'm going to get some information about the meter itself. Where is it located? What kind of meter is it? Is it a meter for a house, a meter for apartment, etc.? So those are my 3 data sets. And if you'll see in the gray box, that is always going to be the code that I would write in a notebook. And everything else is going to be results. So I'm not going to leave out any code. Everything I would write in a notebook is right there in that gray box. So first thing I'm going to do is I'm going to import VerticaPy. And I'm going to grab the stats and I'm going to call it ST to just make my life easier. And then I'm going to put my 3 data sets in a data frame and I'm going to have a look at them in my Jupyter notebook. And if you see that little V with the like Python kind of thing next to it, that's our VerticaPy icon. So just to let you know what you're looking at. It's cute. I like it. And then, so I'm going to look at that. And now the next thing I need to do is I need to join these 3 data sets. In particular, I need to join the data set on how much was consumed and put it together with the data about the meters so that I can see about the same time what was about the same. And I'm looking at the weather here. So I'm comparing at about the same time that I got this usage amount, what was the weather like? What was the temperature? What was the humidity? And the thing about it is, you're not going to get identical. It's just not going to be identical. Date times always vary a little bit. So I'm telling the database to interpolate one of the date timestamps and just get me the closest match that you can on those two data sets, and then show it to me. Now, the next thing I'm going to do is I'm going to get some aggregate statistics. I'm going to look at the min, the max, and then I'm going to I'm just looking at the meter data set right now. So I'm going to figure out where are these located, and I'm going to do a scatter plot with a really simple geographic information on the UK and Ireland, so that I can see kind of where the meters are. And what I'm going to do looking at this is I want to cluster my meters by which sort of municipality they're in approximately. And I'm looking at that, and it looks like there's about 5 clusters. So I need a K for K-means is really what I'm looking at. So I want to do an elbow graph just to make sure my K is good, to verify it. Yeah, 5 looks reasonable based on this elbow graph. Remember the little gray? I mean, all that was one line of code, but anything that's in that gray box is going to be code. Everything else is what's going to display on your Jupyter notebook when you execute that code. So the next thing I'm going to do is using 5 as my K. I'm going to train a K-means clustering algorithm, and it's going to give me some information. And just in case I already had that model, I dropped it, and then I checked the fit. So let me see. So I gave some colors to the various clusters so I can visually see them easily when I did a plot. And I've predicted using that K-means on that data set, which is the same one that I trained on, so it should be fairly straightforward. And then you see 5 different clusters and what they look like. And that's about what I was looking for on those 5 clusters. All right, so now I'm going to take the 3 different data sets. I'm going to put them together. I already joined 2. I'm going to join the other one. Now this is a good example if if one data set came from a third party. Maybe you got your weather from someplace else, and you had your meter data and you want to join that in. That's a good example. And that's what this is. This is just like pulling in the next data set. And keep in mind, it's like Python's not doing any of this work. Even though I'm writing Python, the database is doing all the work. Python is just passing instructions to my database engine. So the next thing I'm going to do is I'm looking at some stats, and it looks like I'm missing a few values on my, just a few, not very many on my meter readings. So I'm just going to drop those. Those aren't really important. There's not enough of them to matter. And then I'm going to save the data. I'm going to put it into a table. Now this is cool because I have joined all my data sets. I've done a little bit of data cleaning, and now I have a nice clean data set, and I can save it as a table, and that data set is now available for other kinds of analysis. I don't have to do this again, ever. It's saved in my database, and I can do intermediate analysis. I can hand it off to the BI team, and they can do analysis on that data, whatever I want to do. And then I'm going to take this new data set, and I'm going to put it in a virtual data frame. Now, what I want to do is my new data set, now that I've joined everything in the universe, I'm going to set it so that it's in 30-minute time intervals. Now, maybe all of my readings weren't in 30-minute time intervals, and that might leave me with some gaps. Because, if I have some things that are in 2-hour time intervals, everything between is going to be blank. It's like, well, I got to interpolate those missing values to give me a nice data set to train the next algorithm on. So what I'm going to do, I'm going to interpolate them. And I'm telling it to use linear as my basis to interpolate those values. So, and then show me the data set. So now I'm going to, now that I've aggregated it to my, now I'm going to aggregate it to my preferred granularity. Before it was like every 30 minutes. Okay, every 30 minutes is fine, and now it's all consistent. And I can save that, and that's great. And now I have that data. And if I need that level of granularity again, I can go back to that table and use it. But what I want to look at next with my regression algorithm actually requires monthly granularity, which means I got to take all those readings that were like every 30 minutes, and I got to aggregate them to show me a complete month's worth of usage for each meter. So I do that. There's the code. All right, and I just pick 3 kind of random data sets, and I just want to look at what does the consumption look like over different months. And what I'm kind of seeing is a little bit of a trend where during the winter or during the summer, the households use less. In Ireland in the summertime, the weather's pretty mild, whereas in the winter it gets kind of cold. So that's when my energy usage is going to be relatively high. Okay, so that's kind of my impression of exploring a little bit of the data and looking at it in some graphs. First thing I want to do is I want to make sure there aren't any outliers, like just crazy different things. So I put in some from some simple code, and I see that little tiny, like 4 lines of code. That's it. Boom, done. All right, there's my outliers. Got them. Let me see them. Oh yeah, I'm getting some peak usage that's way beyond what expected. Again, it looks like it's all during the winter months. That's interesting. So maybe it's not weird data and there's nothing wrong with that data. It's just unusual. Somebody's using a whole heck of a lot more energy in that time period. All right. So we'll leave that. We won't take those out. Now, because we want to do a regression algorithm, it doesn't like categorical variables. It would really like for all of them to be binary, yes, no kind of variables. So what do I got to do? I gotta use one command that says one hot encoding, and boom, all of my categorical variables are now binary. Boom, pow, there it is. And keep in mind that this is not a sample. In this case, my data set is actually kind of small. But if I was doing this with a data set that was 100 terabytes, which if you're looking at smart meter data, that data gets big fast. That's not unreasonable. That would finish in seconds because I'm using the power of a distributed database, which is used to dealing with data at that size. I'm not trying to do this all with the, with the RAM power of my laptop. So now I'm going to look at feature correlations. One line of code, boom. And I looked at all the values and I'm like, show me the matrix, okay? And that actually doesn't require any more code because it does in fact show you the values in the Jupyter notebook with VerticaPy and the matrix at the same time. So you can see them, and it looks like there's something interesting going on in that upper left quadrant. Yeah, let me zoom in, and of course my video is kind of covering part of it, but you can see that there is some really cool correlations, in particular with month and temperature and with your value, which is what you're trying to predict. So let's zoom in on that. So let's just look at my predicted value is value, which is how much energy I used, and then all the things that predict that. And in particular, those first few things, which, is like your temperature, your humidity, your month. Now, we can see that month is really well correlated. I mean, I saw that when I first looked at it. I could see that, December used a lot more energy in general than May. And that's accurate, but the month didn't caused that. I mean, I don't change my thermostat. Oh, look, it's September. I should turn up my thermostat. It's like it's based on your temperature and humidity and things like that. So, but those are based largely on your month. So that's why you get that nice correlation there. So that's correlation and causation thing. So let's aggregate it all. And let's just look at one graph that shows all of it by month. That really shows that that's really obvious, that in the winter I use a lot more and in the summer I use a lot less. It just makes it super clear. So what if I just predict based on is it a winter month or is it a summer month? Just something that simple, and do my prediction. And look at that. That's a pretty darn good prediction. That's pretty accurate. That's awesome. But I want to see if a regression algorithm will do something better. So I train a regression model. I've already got my data set. It's already in my virtual data frame and everything, so I can just tell it, here, go, and here's your predictors. Here's your model. Here's the data that you need to train on. In case you already had that model, throw it out. Here, save this new one. And then give me some info on it. All right. Well, we did train the regression model. And now we're kind of looking at the value predictions is a little bit scattered. Might be some heterodicity in there, assuming I said that right, because that's a tough one. But you know what I mean. There might be more variance based on temperature. So what am I going to do? I'm going to do a Boris-Pagan test, and I'm going to have a look at it. And it doesn't really tell me anything. It's not really useful, but it took me like, 10 seconds to do it. So, all right. So I tried, and I got a little bit of information. And now I can predict the usage using my regression model. And this is not too bad. D's and R squared, everything looks, that's not a bad model. I could use that model. Now, what am I going to do to predict in production? Because do I have to now take that model and go and rebuild it in something else? No, it's in the database. I saved it in the database even, right next to the data that trained it. So what do I got to do? I just got to move it from my dev database to my test database and try it out with some different data and then push it to production when I'm happy with it. That's it. That's all there is. There really, because the environments are the same, there just isn't hardly anything. It takes minutes, not months, minutes to deploy your models, and that's powerful. So, end-to-end machine learning process in the database, data exploration, data preparation, training your model, evaluating your model, deploying your model, scoring your model, all inside the database. And I can use what makes me most comfortable. I can use SQL, I can use Python in a Jupyter notebook, I can use R, and I can import and export PMML from other things. Spark, we even have a really nice connector to Spark. So if you want to take your RDD and you've done some of your data prep, you've pulled all your data sets together, done some joining and transformation and things like that in Spark, we can pull it right from the RDD into the database, and that makes your life easier. Or you can do a lot of the querying and training and things like that on external data. So that's what I got. I wanted to bring one little quote. I do a cool webinar series called the Data Disruptors, and these are different companies that do things with the database, and they accomplish some pretty amazing things. And the last one I did was with Xiaobo Ge. I hope I got that right. He called me Peggy, so I figure we're even. We both butchered each other's name equally. So previously we used Apache Spark. He used Apache Spark, and 80% of the time that Spark uses is just to take the data off the disk and put it in memory, and then 20% of the time to actually do what it needs to do. And putting it in the database saved him 80 to 90% of that writing time. So he saw some huge benefits of moving into the database. Hopefully you will too. So now I'd like to go to questions. And if you want to give this a try, it's available online.